when I first was, doing my YouTube browsing, and I came across this guy, Wolfie6020, and watched this video. First of all, I have to say that I was really surprised that he even admitted that pilots have to compensate for the curvature of the Earth. But all that aside, let me backpedal a little
You
bit.
mean that they don't have to compensate?
No,
That they
but
do?
we'll talk about that. So,
Okay.
so when I started looking at the math, I started doing my own math, and I was coming up with these really crazy numbers, right? And this is very reminiscent, Jern, of the time that, we were looking at circles and curves and saying, well, gee, it doesn't seem right that you would describe a sphere in exponential terms, in terms of exponents, as in 8 inches per mile squared, because like you said, and I agree with you, if you are constantly in a state of turning or a constant curvature, then you would think that there would be a very specific number that you could apply to this. Well, it turns out that no, that's not true, which is really pretty bizarre. But so anyway, after I started doing the math in the way that I understood it, I was coming up with numbers that were absolutely beyond outrageous. And so I said, you know what? I'm tired of arguing with people that think they know what they're talking about in math, or, know a little bit about it and can go on. So I said, I'm going to go online, and I'm going to find a math wizard, right? So I went online and I found one particular site, and the reason that I chose this site is because they claimed that their tutors, or their people that were doing math, were graduates of Ivy League universities, meaning Yale.
Red flag, red flag. No.
Right. Oh, and we're about to find that out as being true. But yeah. So let me continue here. So anyway, so I got in touch with the first person, right? And I actually wound up talking to a total of 3 people from these, with master's degrees in mathematics, or also engineering. And I also talked with Charles Flat Earth Math, because I wanted to get, kind of the heavy Glober perspective, because these people were unbiased. They were not flat earthers, they were not ball earthers. And in fact, the way I phrased my questions, and when I was discussing it with them, I left no hint that I was even looking at, being a flat earther or anything like this, because I wanted to keep it completely impartial.
Of course
Well,
not. Nobody wants to be freaking locked up in the nut house.
right, exactly. So that's the way I approached it. And so let me tell you what I found from 3 people that were essentially equally qualified. The first person looked at the way I was doing my math, and although he said what the other said, as well as what Charles said, that there was really no way you could define a constant in an equation, so to speak, your next best bet to calculate it is to do it incrementally, and also beyond incrementally in small increments is probably the most accurate way. And I agreed with that, and that's exactly how I did mine. So he was, we started talking a little bit more, and I think it kind of hit him, the implications of what were being said there. And I didn't say anything to him, but he said, this kind of seems so crazy though, that I'm not entirely sure that it's right. And he said, I can't charge you for it, and I'm not going to charge. And he did not charge me for it, to his credit, right? Because it baffled him almost as much as it did me, even though he understood, using the tangent and the sine arguments and all that stuff, all that math. When you looked at it from a different perspective, in the exponential form, and looked at these distances, also the big picture and the small picture, it really didn't add up. And one of the things that, I kind of threw towards him was that, you can look at this from a big picture standpoint and from a small picture standpoint. And really what I think it comes down ultimately is your frame of reference and how you're looking at this. And of course, obviously the flat earthers have a completely different frame of reference to how they're looking at this curvature issue as the ballers are. And both, believe it or not, and I have to credit Charles for this, have, a reasonable argument for them, okay? And I have to say that out of all the tutors, out of the 3 tutors and Charles was definitely the most helpful in helping me to understand a concept that would kind of bring the Glober point of view into focus a little bit better. And that was actually something that you said a while back, Jaren, and that is, you know, if you are to look at it as if you're driving in a car and you turn your wheel and you leave your wheel turned to one position, you're going to go around in circles and basically track in your own tire tracks, right? Mm-hmm. And I looked at that and was like, okay, that makes sense to me. I get that, you know. But then again, when you're looking at curvature and you're talking, you know, with the ballers, and they're saying, well, if you're standing on the shoreline and you see the a boat going over the horizon, that means it's physically dropping vertically down on a z-axis, right? And that's why it's leaving your sight. Now, of course, there's a lot of controversy on that, but nevertheless, the Globers are hanging on to that argument. Therefore, we must assume then from the perspective of the person standing on the shore that if you were to kind of magically fly out there, that you would have to descend down over that curvature to be able to get back up and catch up with that ship, right? Okay, cool. Well, so anyway, let me kind of continue on with my tutors. Now, the second tutor that I had, Svetlana, who is also a master's in mathematics and engineering and physics, by the way. Well, I think she also caught on to what I was, you know, what my math was showing. And she started, this was crazy, she started using gravity and bringing gravity into the equation. I'm like, wait a minute, Svetlana, what does gravity have to do with describing a sphere mathematically and what kind of curvature? And she goes, oh, it really does have an effect and all this stuff. Anyway, that turned into kind of a cluster screw, to say the least, and we didn't get very far. And then, of course, then there was a third person who came to the conclusion that, yeah, it needs to be done in small increments. That's really the only way it can be expressed. And then there was Charles, which ultimately, you know, said that, well, you simply cannot, it's not something that you can calculate. And Charles actually said to me that the typical baller argument, and that is, well, you don't have to compensate for it because you're kind of always doing the compensating all the time automatically. Gravity does that for you, right?
You're talking about in terms of aviation and flight.
Exactly,
right.
Which I thought was funny, especially since I see this comment from Charles where he says yes. So that is quite the stark contrast of what he told me previous to that, but that's really neither here nor there, because I think that, you know, we know that people are guilty, and even we've done it where we will use certain facts to our, you know, advantage, if you will, okay? So ultimately what we came up with is, you know, out of 4 different people, I essentially came up with 4 different points of view on it. And, you know, how is that possible? And that really makes me wonder, because if all these people are trained in the same mainstream you know, math and physics concepts, then how could they all have such, you know, vastly differing opinions? And one of them, the first guy, even agreed with me that, you know, from a specific perspective or frame of reference, that my analysis of, if you take a 24,901 mile circumference sphere and you travel 1/4 of that circumference, which would be 6,225 miles, you have also traveled down the z-axis, you know, coming straight down vertically, of 3,959 miles, which is, of course, the radius of the Earth, right? Mm-hmm. That is absolutely undeniable from a specific point of view. There's no way that you can deny it, period, right? If you travel that forward. Now, Charles sent me a rebuttal to that today, saying that, well, if you take a moment in time or a static frame of reference, then all of a sudden you can see that what you're doing is you're incorporating the z-axis and making it the same thing, or the x-axis and making it the same thing as the z-axis. And of course, my response to that is, no, that's not true, because what I'm actually doing is when I'm calculating the position of the plane on the sphere, I'm actually taking a vector between the x-axis going forward and the z-axis going down, and thus I'm seeing the curvature of the Earth, okay? So, but again, he wanted to bring this back to a static frame of reference. Well, unfortunately, we don't live in static frame of references. Everything is in motion. So I guess the ultimate lesson that I got out of all this, and like I said, I do have a much better perspective of how the ballers see it, even though I do not agree with it. There are, certain ways that you can look at it where the math is so outrageous, like in an example I just gave, that it comes back with a 0.636 to 1 ratio. If you're going 62.25 forward and 39.59 down, that works out to a 0.626. And of course, Jaron, you were talking about your 0.318 and all that. So we're going to just leave that behind, and we're not even going to go there, okay? Because yes, I fully understand that there are many other ways to look at this, but to discount that particular point of view is folly, because from a certain perspective, it's undeniable, okay? So let's move on a little bit. So all this is all well and good, and I will show some of the actual math calculations that I have, but before that, what I want to do is I want to play these videos from Wolfie, and Wolfie has given me his permission 100% to do this. And thank you very much for that, Wolfie. And it's great. So Wolfie is, let me tell you a little bit about Wolfie 6020. He is a corporate pilot, flying a corporate jet. I don't know if he has any airline experience or what, but he does have the rating, which is called the Airline Transport Pilot or the Air Transport Pilot, ATP. Both certified in Australia or New Zealand. Anyway, his country of origin. I forgot what he said, it's down here somewhere, and also in the United States. So he essentially holds a dual ATP rating. Well, if you're going to look at pilot certifications and compare them to college degrees, then Wolfie would have the PhD of pilot's licenses. As compared to myself, I would have, as a commercial pilot, would be more akin to a master's degree, and then somebody like Chris Van Maitre, who has a private pilot's, would be akin to a bachelor's degree, and then the associate's degree would kind of be related to the recreational pilot grades, which are a completely different story altogether. So anyway,
if I'm afraid of flying.
You would be probably smarter than all of them in some ways. But anyway, so really what this tells me is that your credentials on something really don't mean jack, right? Because here we have all these people, Charles and Svetlana and Nayaz and I forgot the other guy's name, and they all have pretty vastly differing opinions, and there's some points where they cross over and they're agreeing with each other, but of course that doesn't really make a whole lot of sense considering that all of the quote-unquote experts were trained by the same system, as was I, but I obviously look at things very differently. So anyway, so getting back to this video, Wolfie makes his argument. We're going to play this video in its entirety, but before we do that, I want to make the comment that one of the things that he uses as his proof for this is he has put this video out in which he is stating that here's the proof, the autopilot is automatically adjusting the attitude down to compensate for the Earth's curvature. All right, great. So let's look at that really quick. I'm going to go ahead and play this, and let's just watch it. So what we can see here is we've got this little point right over here, which is the level, and it comes to the end of the arrow, and you can see this little fat part is starting to drop below this like little horizon line. Now, what happens is it will pitch, and it will level itself out perfectly. Now, if we look at this, the plane is flying at 41,000 feet, and it stays there dead on the money, okay? So what happened there? Well, he's claiming that the aircraft has sensed a drop in the curvature of the Earth and has since compensated for it. So let's watch again as he goes back. And now one thing I also wanted to point out is this right here. Now this instrument is called the VSI, or the vertical speed indicator. And what it is showing is it is showing an absolute dead level flight, 0 foot per minute climb or descent. It's not showing anything. And of course, we just saw the autopilot supposedly correct for, you know, some sort of Earth curvature. So let's watch. And here he's going to claim that it does it again. So here we are at 40,000 feet, staying right on the money. We are not going anywhere, and I mean it is right on the money. And obviously, he is in autopilot mode, as he claims, you know, in this particular shot. So he's going to pop back up, and he's going to say, watch, it's going to do it again. Now, he says that this autopilot is making this correction hundreds of times every minute. Well, we're not really seeing that, first of all, for one. So here it is. You got a slight discrepancy right here, and then you're going to watch it go pop right back onto level. All right. So what he's saying here is that he's using this as evidence for the autopilot compensating for the curvature there. Well, first of all, I say BS, and here's why. Because when you're flying along any number of things, and he will state this in this video, by the way, so keep listening for that. But when you're flying around, any number of things can cause the aircraft to slightly pitch up, pitch down, or if you happen to fly into what's called a thermal, which is a rising column of air, it can cause the airplane to ascend vertically without really even giving a nose-up inclination, right? So all kinds of things can do this, and of course, when that happens, you will see either a slight change in the VSI, the vertical speed indicator, as well as typically a rise in horizon on the artificial horizon, okay? So all of our instruments are going to agree with us. So for him to sit there and categorically state that this compensation that is going on is a result of the curvature of the Earth is about as dishonest as you can get, because there is no way he can prove that. And in fact, it's much more likely that what's happening here is the autopilot is simply compensating for the normal jitters of the air, you know, thermals, turbulence, whatever that cause.
That's what I was thinking. Yeah.
Exactly, and because that is in fact what is happening. This whole using that as proof that the autopilot is just unbelievably dishonest, and it's ridiculous. Okay, so what we're going to do is we're going to go through this video, and I'm going to make little stops, you know, kind of like we did with the 5 red pairs videos, and I'm going to throw my commentary in on this, and we're going to kind of see what everybody thinks when this is all done. And then I'm going to show you, at the end of this, I'm going to show you not only the calculations I did based on a the Sagitta and also AutoCAD, as well as the 8 inches per mile squared formula. I'm going to show you those calculations as to what these supposed changes cumulatively would actually show up as, and how this will work. And I've got this all. And then beyond that, we have a special treat. I got in touch with another YouTuber who I'm sure everybody is very familiar with by the name of Rob Durham. And Rob Durham is, of course, another pilot and an engineer as well. And he's also the go-to guy for AutoCAD. He's an absolute whiz at this. And I had him model this in AutoCAD. And guess what? And I'm going to play this. I'll actually play this for everybody. But the AutoCAD modeling basically comes back with exactly the same numbers that I did. And you know, this calls into question this whole compensation of the aircraft pitching to follow the curvature of the Earth. Now, the one thing I do want to say about Wolfie 6020 is that he is probably one of the only Globers in all the time that I've been doing this for the last 1.5 to 2 years that has ever claimed that yes, indeed, you do have to change the pitch of the aircraft to compensate for the curvature of the Earth. Now that is patently unheard of, because typically the Glober argument, and I'm sure you guys know it well, is they say, no, it's fully automatic, just like Charles told me the other night. It's fully automatic, and it's just the gravity in and of itself that changes the orientation of the plane, because you're always referencing from a center point in the center of the Earth, right? That is what all the ballers have argued, and other pilots as well. So I thought this was quite the enigma that Wolfie came out with this and said that you do have to do it, and then used this completely phony, you know, and it's not phony, it's real, but to categorically state that, oh, here it is, you know, compensating for the curvature of the Earth, is unbelievably dishonest and flat out wrong.
Now,
Okay.
I've got a question now. That is a simulation?
What is what a simulation?
What we just watched, or what
No, it was real. That's him and his.
Okay.
That's him and his
Okay.
corporate jet and his heads-up display.
Okay, so and I got you. So the next question that I had is, now this is the beginning of the video. What we're looking at is a little miniature of what looks like it says U.S. Navy on the plane. So I'm assuming that he's either ex-U.S. Navy or current U.S. Navy, which tells, or you know, he may be a wannabe. But
he's a citizen of another country, Australia or whatever, and of course, you know, I'm not saying that would stop that, but that's he only uses the airplane, John, for just to make a little a graphical point is all. So I mean, let's actually get into the video, and we'll hear it from Wolfie himself, and then I will make stops and make commentary on certain parts of it. So let's go ahead and do that right now.
I'm just doing a short video to answer a question I get asked all the time. And the question is, does a pilot have to pitch the nose of his aircraft down as he's traveling across the Earth? And that is to compensate for the curvature of the Earth. Well, the answer is that the aircraft does in fact pitch down as it travels across the Earth. And no, the pilot doesn't really notice it, because the rate of pitch down is so slow that it's basically imperceptible. And what I'm going to look at is how we actually fly an aircraft by.
Okay, great. So the first thing he said is, he says that it does indeed pitch down. The aircraft does indeed pitch it down. He's not saying the pilot is doing it. He's saying the aircraft is doing it. And of course, because he flies by autopilot all the time, and also showed that demonstration, that he has very suspiciously selected his choice of words, because you're right. If the aircraft is making the pitch down, the pilot probably would never notice it, because it would be such a minute adjustment at the time. However, back in the day, you know, for us old school pilots that didn't really use these type of autopilots, we have to make these adjustments manually. And the way that we have to make these adjustments manually is by keeping an eye on our horizon and a point of reference on the front of the plane, also looking at the artificial horizon indicator, which is the top center indicator that we're seeing there, and also the VSI, the vertical speed indicator, which is the lower right-hand indicator down there, which is currently showing a 100 foot per minute ascent rate on that. But that's neither here nor there, because this is a simulation. All right, so let's go ahead and go on with him.
Reference to the flight instruments. This is what's called a 6-panel, and it's basically a version of what you'll find in just about every aircraft. And I've also got a model of an analog clock here running on the iPad, and the reason for that will become apparent shortly. But I'm just away on a work trip at the moment, so I didn't really have a good aircraft model like I have at home, so I just managed to pick up this little F-18 model from a local toy shop, but it'll hopefully do the job. When I get home, I'll try and make a more professional version of this video, but this should answer the question just for the moment. Try not to be too shaky with the camera. Okay, first thing we need to understand is that the Earth is not as small as many people will think, and your typical airliner traveling at 450 knots will actually take 48 hours to travel around the Earth. Now, obviously, they won't do that non-stop. They'll have to stop and refuel, but that's the actual rate at which.
Okay, now in that, he's absolutely correct, because he says he specifies his airliner speed at 450 knots, and I'm going to, you know, for the Americans, since I'm American, I'm going to convert that to miles per hour. So what I did is I looked up the cruise speed of a 737-800 series airliner, okay? And lo and behold, that cruise speed is precisely 1/2 the rate of the rotation of the Earth. The rotation of the Earth is 1,037.5 miles per hour. Well, the half of that speed is 518.75 miles per hour, okay, which is right on the money of Boeing's specifications for the 737. Their cruise speed, they set it at 518, so I'm adding an extra 3/4 just to keep the math all nice and neat, okay? So, all right, he has also stated that in that 48 hours, it takes to traverse the 360 degrees around the Earth, and he's actually going to show that graphically. And he's correct. He's absolutely correct. And he breaks that down to 1 degree every 8 minutes of flight. Or, if you want to look at it another way, it's 7.5 degrees per hour of flight. Okay? So let's go ahead and continue on.
It's going to travel around the Earth. So if we imagine this aircraft is going to travel all around the Earth, it would obviously have to pitch down and pitch all the way around 360 degrees. That's logical, right? But how long does it take to do that? It takes 48 hours. Now, come down and have a look at this analog clock, and we're just going to watch it for a few minutes. Notice you can see the red second hand sweeping around. The movement is obvious. Can you see the minute hand moving? That's the minute hand. If you watch it really closely for several minutes, you'll obviously see it moving. What about the hour hand? That's the hour hand pointing to the 3. Can you see that moving? That hour hand actually moves around the clock once every 12 hours. So it takes 12 hours to go 360 degrees. When we're flying our aeroplane, we take 48 hours to go 360 degrees. So the actual rate of pitching down, the rate the aircraft has to actually pitch down like that, is 4 times slower than that hour hand is moving. 4 times slower. Now, imagine this was a real clock and we grabbed an ant and we put the ant on the end of that hour hand. Do you think it would feel anything? Do you think it would feel any centrifugal force? Do you think it would feel any movement? Do you think it could actually detect any angular change? Well, the answer is no.
All right. Well, let's look at this a little bit different way, okay? First of all, he is, I know, first of all, he is talking about putting an ant on the hour hand, which is, what, 2 inches, 1.5 inches away from center. And he is absolutely correct in that it would take the clock face, the hour hand, going around 4 times. Now, we all know that the Earth turns once per day, or the equatorial speed is 1,037.5 miles an hour, 1,040 miles an hour, whatever. Okay, so what he has failed to do here is he's not really being too honest, because yeah, what he's saying is absolutely true. Do you think an ant would perceive that movement 1 inch, 2 inches away from the center? Absolutely not. But you know what? The ant is not in the center of the Earth, and neither are we. Okay, let's get real here and let's extend that hour hand out the 3,959 miles to the surface where reality is and where we live, right? And now let's look at that velocity. Well, it's still going to take 4 times. It's still going to take 4 times as long, right? Because we're only traveling at 518 miles per hour. So what you do is you take that 1,040 and you divide it by 4, and you get then the end of that hour hand is now traveling at 260 miles an hour. Now let's put our ant on the end of that hour hand and ask that ant if he thinks that he's going anywhere. I'm going to say, oh yeah, right? So this is a really poor way to look at it. And again, he does this to try and completely undersell everything, to make it seem so absolutely minimal. The other thing that he's talking about is that, you know, yeah, it takes 48 hours to go 360 degrees around the Earth, but what he doesn't say is, but this is implied, is that it only takes 12 hours for the aircraft to go 90 degrees from horizontal to completely vertical, okay? That's a big problem, and that is especially a big problem when you're doing curvature calculations. So again, he's trying to minimalize everything by simply saying, oh yeah, well, it takes 4 times around to even have any effect. So all right, let's move on.
And remember, our aeroplane is pitching down 4 times slower than this. So basically, if I filmed that clock for an hour and then slowed down the video 4 times, that is how much the aircraft is actually pitching down. So it's 360 degrees in 48 hours. What that equates to is 1 degree every 8 minutes. Just every 8 minutes, it's going to go down about that much. Just 1 degree, another 8 minutes, another degree, another 8 minutes, another degree, another 8 minutes, another degree. So the rate of...
Okay, now another thing that I want to point out here is he's insinuating that he's only bumping the yoke of the aircraft and just pitching the nose down like momentarily. What he is not explaining is that this pitch down over the period of 12 hours or 48 hours is a cumulative pitch, okay? Meaning that after 12 hours, he has literally changed his orientation from horizontal to vertical in a matter of 12 hours at the rate of 7.5 degrees per hour cumulatively, okay, to roll this over. All right, so let's go on from there. And again, I said he's trying to minimize this.
Of movement, the rate of pitch down is just so slow that it's not perceptible. The human body has vestibular sensors. They're the semicircular canals inside your ears, and they are designed to detect motion, but they're not completely infallible. And in fact, the reason you get dizzy when you spin around too much is because they are quite easily fooled. They're not sensitive enough to detect any motion that is less than about 2 to 3 degrees per second rotation. So I'll say that again, 2 to 3 degrees per second. Now, if we're moving in our aeroplane and we're only changing pitch attitude by 1 degree every 8 minutes, that is many hundreds of times slower than the threshold at which your human body can detect motion. So there's just absolutely no way the pilot or the passengers are going to feel anything.
Okay, and you know what? On this point, we absolutely agree. Your vestibular senses are exactly as he's defined, and we will not perceive such minute changes in orientation. It takes something much greater for us to actually notice it. However, what he fails to point out again is that the aircraft instrumentation will absolutely register that change. In fact, it'll register it in a really big way, and we're going to be demonstrating that here shortly. So, you know, like I said, I agree with this. You know, you wouldn't be able to sense it with your own senses, at least not the average human being. But again, the instrumentation is going to register those changes in a foot per minute, it's going to be a foot per minute descent rate, okay? So there we go. So we finally come on a point, and actually I agree with him on virtually everything he has said. His numbers are correct. The numbers that he's using, the math that he's giving are correct, but he is dramatically underselling the implications of this math. So here we go. Let's keep going.
Okay, now let's talk about why the pilot is not actually conscious of pushing the nose down continually. Remember, I think some people must imagine the Earth is tiny and that you actually have to fly around like that. It's not that small, you know. As I said, it takes 48 hours to go right around the Earth. But anyway, I'll talk a little bit about how we fly an aeroplane. And what I'll do is I'll focus on an airliner. We'll use examples for airliner speeds, which are cruising at about 450 knots. The artificial horizon here is what we call the primary attitude indicator. And when you're flying a large commercial jet or a corporate aircraft, high performance aircraft, you're referring to that instrument primarily as the reference for your aircraft attitude. Now, to combine with that, we've got a number of other instruments, and the two we'll focus on are the altimeter, which tells us our height, and the vertical speed indicator down here, which tells us if we're going up or down, you'll see that orange needle. It can actually deflect upwards like that when we're climbing, and it will deflect downwards when we're descending. And the altimeter is basically like it's got a couple of arms, you know, depending upon the complexity. This has got a single arm for hundreds of feet, and then it's got a digital readout for the thousands of feet. But basically, if we were climbing at 1,000 feet per minute, that orange needle would be up here pointing at the 1. And if we were climbing at that rate, this needle would be moving around this dial 1 revolution every minute. We're climbing at 1,000 feet every minute.
And he is correct.
Now, when you learn to fly, I don't know how many of you are pilots or ever wanted to be a pilot, but when you're flying an airplane manually, you are constantly referring to the attitude indicator, the vertical speed indicator down here, and the altimeter, and you're monitoring them at all times. Now, if we're trying to fly level, if we're trying to maintain level flight, say, for example, 35,000 feet, okay, we want to keep this needle stationary. And if we start to see this vertical speed indicator needle moving up or down, we're going to make an immediate correction. Okay, so if that just started going up slightly, we're going to push forward on the joystick or the control yoke, and we're going to push the nose down just slightly. And what that's going to do is just arrest that rate of descent. Now, when you're flying, when you're hand flying, it's just a constant dynamic process. You're scanning the instruments, you're making minor corrections all the time. Literally every minute, you're making maybe half a dozen or more minor corrections. Now, traveling at 450 knots, just 1 degree of pitch. Now, you'll see that little orange dot at the middle, okay? If we move up to that first white line, that's 5 degrees of pitch. Now, we move up to the second one, that's 10 degrees of pitch. If we pull the nose up just 5 degrees while we're flying at 450 knots, we're going to be climbing at many thousands of feet per minute. Okay, it's going to be climbing very, very fast rate of climb. So when we're cruising along, maintaining altitude, we don't want that to move more than a fraction up or down. So we're making slight corrections to the pitch attitude, and it's literally less than a degree, less than half a degree, in fact. If the aeroplane is being flown by autopilot, the corrections are so small that they're basically imperceptible to the pilot. You know, every time the autopilot detects just the tiniest climb, and this altimeter moves off its desired altitude just by 10 or 15 feet, the autopilot will make a correction and it's going to push the nose down. Okay.
Okay, so let's talk about that. First of all, let's just say that he refers a whole awful lot to the autopilot flying the airplane. And as a result of this, he keeps making the claim that the pilot is never even going to be conscious of it. In fact, he's flat out stated it. The pilot will never notice it. He'll never be conscious of it, yada, yada, yada. But
yeah, I thought that was kind of odd. Like, how could you not notice, like, consciously making a correction, right?
Well, that's it. And that's the thing. I mean, but if you're not using autopilot, then you, the pilot, have got to make those changes, right? Now, here's one thing that I'm going to say, and I know that every pilot out there knows this is absolutely a true fact. And that what he is implying here is that, well, what he has flat out stated is that ultimately, whether you do it via a kind of a multitude of times, making minor pitch adjustments that ultimately add up to 1 degree every 8 minutes or 7.5 degrees an hour, he is saying that this is something that is ongoing forever. All right, you have to constantly do this. Now, I can tell you as a pilot, this is not true. This is absolutely not true. And in fact, and every pilot in the world will back me up on this, once you get to your cruise altitude, if you have a relatively calm day, you know, no high winds or, you know, thermals or anything like that, and there are a lot of them, once you set your elevator trim or your pitch trim, you can pretty much not even have the autopilot on, and that airplane will fly straight and level for miles and miles and miles and miles, 20, 30 minutes. I've had it do it, never even had to make a correction, and never in all that time did the aircraft vary more than plus or minus 50 feet, okay? So that right there tells you that, gee, even without an autopilot, somehow the airplane would be correcting itself automatically, just like normal globe earthers make the argument that it does, right? But Wolfie's not making that argument. Wolfie is saying that the pilot has to do it, and if the pilot doesn't do it, then the aircraft autopilot will. All right. So
that's right. He is making that admission, isn't he?
yes, he absolutely is. He's flat out stating it. So, all right. So let's see. He also makes a statement a little bit earlier, which I forgot to address. He says, well, the Earth really isn't that small, right? So this is why we don't notice these things. And yet, you know, this goes back to the old argument of really, so if the Earth isn't really that small, then why do the ballers make the argument that a ship drops over the horizon in somewhere between 3 and 6 miles when you're standing on the beach? That's pretty small. And I got news for you. When you're in a 737 flying at 518.75 miles an hour, you are going to have a significant amount of drop in just well, within a minute. In fact, if you do the curvature formula, you're going to have automatically a 50-foot drop in the first minute. And as we know, it becomes exponential from there. So regardless of how Wolfie wants to talk about this, he is still saying that no matter what, because of the curvature of the Earth, you are still having to force the nose of that plane down, which is absolutely not true. Okay, so let's continue on.
Okay, so it never allows the altitude to deviate so much. So now what we've got is a situation where either being hand flown, the pilot is making the corrections manually to maintain the altimeter steady, maintain the vertical speed indicator at 0. It's resulting in incredibly small pitch changes, less than ½ a degree. That's all you're doing. So it's very, very small when you hand.
Right. Now, let me say this also. The pilot obviously is not going to be as efficient as the autopilot is, because he's right about the vestibular senses. Okay. Most pilots, you know, like I say, especially when you're flying VFR, you pick a point on the horizon as a reference and you just look at it. And half the time you don't even have to look at your instruments, because you can simply gauge that you're straight and level flight by picking a point on the horizon and following it. Okay. In fact, this is something that they teach you to do day one of flight school. Okay. So, he's basically, you know, kind of muddying the waters with all this. And again, he's trying to imply that you're just bumping that yoke, you know, every few seconds, and it's correcting this upward pitch with respect to the Earth, you know, and you're having to do it all the time. Well, so if you're not using your instruments and you're not glued to the instruments every second of the time, you can't really count on your vestibular senses to be able to tell you that you are diving at, you know, certain rates of speed, especially when that dive comes on very, very slowly. You know, at the rate of, well, I'll show you what the math shows. But believe me, it does come on rather rapidly, especially exponentially, you know, using the 8 inches per mile squared or the Sagitta. All right. So again, like I said, he is absolutely saying that there must be a physical adjustment every few seconds to compensate for the curvature of the Earth, either by the autopilot or the pilot, which is flat out not true. So let's continue on.
And flying, when the autopilot is flying, it's making rapid, tiny corrections, sometimes 0.1 of a degree. You know, I've actually got a head-up display in the aircraft I fly, and it has a much finer resolution of the pitch scale on the aircraft, and I can see 0.1 of a degree pitch deviation. When it's on autopilot, that 0.1 of a degree, it's constantly adjusting, just like when you're driving down the road. You're driving down the road, even if the road is straight, you don't just hold the steering wheel straight. You're making just the tiniest adjustments all the time to keep the car in the middle of the road, and that could be.
Yep, and that's actually a pretty good analogy from a car. However, when you are dealing with a curvature that is falling away from you at an exponential rate, then common sense would tell you that you would have to keep a constant pressure on the yoke, pushing the nose down. Here, a good analog to it would be an aerobatic pilot, okay? and I've done a little bit of aerobatics myself, so I can definitely speak to this. If I go to do a loop, all right, a regular inside loop, I have to pull back on the yoke and hold that pressure back so that the airplane will nose up and ultimately become inverted and then come back down on the other side, okay? But it requires holding a great deal of pressure on there. And conversely, if I do an outside loop, I have to press down on the yoke and hold that pressure and even increase it as I'm going around in the outside loop. So this is kind of the same thing. Obviously, if we're talking about ultimately doing a loop that requires 48 hours, but the bottom line is he is saying, and also the physics of it demand that you would have to be pretty much applying a continuous physical pressure downward to maintain the conformity to the curvature of the Earth, much in the same way that when you are driving in your little red Corvette around in circles and you have to turn the wheel to the left 90 degrees or whatever, you have to hold that wheel there. You can't just let it go, because what'll happen, it'll straighten out and go straight again. So you have to hold that wheel. So this is the same exact analogy again. So let's continue on.
Due to maybe a few bumps in the road, or perhaps a bit of side force from wind. In the aeroplane, there's any number of reasons that your altimeter can just start to fluctuate up or down a little bit. Very slight air pressure changes or turbulence. You know, when the autopilot is flying, it's making numerous tiny corrections all the time. You know, 10, 15, 20 corrections every minute that are so small, they're not perceptible, and they're just holding the altimeter steady. You barely even see the vertical speed indicator move. So we're making tiny corrections all the time to compensate for the curvature of the Earth. The nose has to only pitch down 1 degree in 8 minutes.
Cumulatively.
In that 8 minutes, the autopilot has probably made well over 100 or maybe even 200 individual slight corrections, you know, slight corrections of 0.1 of a degree or 0.2 of a degree.
Right, and that's assuming the autopilot is doing its hundreds of corrections. Now the pilot, because of the fact that, well, we're not really going to be reacting that fast necessarily, and you know, when you fly not on autopilot, you will have more of a deviation from your assigned altitude, plus or minus. But even if you only check it every 15 seconds or every 30 seconds, which actually is quite a bit, and you really don't do that because, like I said, once you set your trim, you honestly don't even have to look at it unless you're in turbulent conditions for 10, 15, 20 minutes. It'll just keep flying along, no problem. Why? Because an object, you know, going in a certain direction will kind of want to stay going in that orientation and direction, you know, automatically. And that is, in fact, what actually happens. So let's go back to Wolfie here.
If there's any climb detected, the aircraft just pushes the nose down by 0.1 of a degree. You won't see it, you won't even feel it, but it's basically absorbing that 1 degree of pitch down all the time as it's making these minor corrections. So yes, so the reality is, as the airplane flies across the Earth, it is pitching down. The pilot's not conscious of it because he's not even thinking about it.
Really, unless he's actually flying the plane, then he's very conscious of it and he's absolutely thinking about it. You know, me thinks that Wolfie flies by autopilot way too much, and he's one of these people that ultimately is going to wind up, you know, flying off someplace without enough fuel. So, you know, just keep that in mind. He's attributing everything, oh, autopilot's got it all taken care of. Sorry. But, you know, there are some of us who actually still fly airplanes without the autopilot.
The rate of movement is so slow that it's negligible compared to the smaller, more frequent corrections that you need just to maintain altitude, just to maintain the vertical speed indicator steady. And obviously when the autopilot's doing it, pilot doesn't even have to touch the controls. You virtually don't see any movement in this artificial horizon. In a head-up display, if you look carefully, you can see tiny deviations in the pitch. 0.1, maximum 0.2 of a degree, you know, as it compensates for turbulence or updrafts or even this curvature of the Earth. It's just holding a steady altitude the whole time.
Right. And by the way, what we witnessed on the first video was the autopilot doing just that, compensating for small turbulences, thermal air rising, crosswinds, whatever. That was what we were actually witnessing, not the autopilot compensating for the curvature of the Earth. That is just ridiculous.
These instruments work on air pressure, and they're sensitive enough to notice just slight deviations, and then the autopilot will correct immediately. So basically, the whole time I've been talking, you see that hour hand has just moved maybe 2 or 3 degrees at most. If we slowed that down 4 times, it hasn't even moved 2 degrees. And that's about the rate of movement that the aircraft has to pitch down. So hopefully that explains, first of all, why pilots don't really notice it, and why passengers absolutely cannot feel anything, and how it is basically just absorbed in the normal method of flying and maintaining altitude.
Okay, and again, the last part of that was right. The passengers aren't going to feel it. The pilot won't notice it unless he's watching the autopilot, because he won't be feeling anything. But if he's flying the plane, then he will absolutely notice it, because he himself will be having to make those corrections. Now, let's now look at what some of these curvature formulas are that he's claiming that he has to compensate for. All right, so what I did here, I did this 2 ways. Well, actually, I did it one way. Rob Durham did it another. And I'm sure Flat Earth Math, or any of the math wizards out there, maybe Red's Rhetoric channel
I actually just did it too on my side too, so maybe we can compare notes as well.
Okay, so cool. So the first thing I want to point out is that I took this airline speed of 518.75 miles per hour, right? And in 1 minute, it has traveled 8.6458 miles, okay? Curvature, z-axis in feet, is 49.83 feet. Average foot per minute drop, 49.836 feet, right? Makes sense.
That's the same that I got.
Yep, absolutely. So now, just for fun, I took it and I did it at double the speed, supersonic, and it's interesting because you're going faster and you're covering more of the curvature. You've gone now 17 miles, 17.29, which is exactly double the distance traveled. Makes sense, okay. But the curvature, because of the fact that it is an exponential function, because it falls off faster the further you go out, has now dropped to 199 foot per minute. Now, obviously, we're talking about an airliner here, so this is kind of moot, but I just wanted to throw it in there just for, just for funsies, okay? Now, at 2 minutes, we have gone the same as the double the speed on the 1 minute, 17.2917. The curvature feet and z-axis, of course, remains the same, but because of the fact that we're doing it in 2 minutes instead of 1, the average foot per minute drops to 99.672. So then I started kicking it up, and I originally was doing this in like 15-minute increments and then dividing it down, but then I said, oh, hey, wait a minute, Wolfie's doing it 1 degree every 8 minutes. So let's see what happens in 8 minutes if you do not compensate for this curvature. Okay, and I'm saying if you do not compensate for this curvature, right? Well, according to Wolfie, if you don't touch that thing, you just let it fly off, then in that 8 minutes, you've traveled 69 miles, and the Earth has fallen out from underneath you at 3,189 feet, okay, giving you a average foot per minute of 398.6690 feet in that 8 minutes. Now, I got to tell you guys, when you're dropping at 400 foot a minute, that's akin to a pretty healthy glide approach to the airport. That's probably something like what they would do starting their descent into a city. And it takes several, it takes a long time. Sometimes they'll start their descent half hour out, 45 minutes out, whatever.
Well, I got 2979 feet per minute and 178,779 feet per hour. So let's say you had a lazy pilot that forgot to do this, constant angling of the nose down, then within an hour they should gain an altitude over 178,000 feet.
Yes, that's true. And thus, of course, this is why my math experts told me that, that margin of error becomes greatly reduced the more frequent you compensate for these curvature changes. And he's right. Okay. And Wolfe is also correct in saying that, you know, obviously the autopilot's doing hundreds of times a second. But the pilot is not going to be doing it that much. But the whole thing is
right.
that we can see,
and if because he would be conscious of it. I totally disagree with what he said, that the pilot would not be conscious of making these corrections, because by definition, noticing, you know, something that you want to correct for, and then correcting it is a conscious decision. A pilot is definitely going to be aware of that. So my whole point is if again, if a pilot forgot to check his horizontal for an hour, then he should, and this is something that could be tested, and I guarantee you it's not going to happen, but if the Earth was a sphere, then he should technically gain 178,779 feet, assuming that they're traveling at the 450 knots or 517.851 miles an hour.
Right. Okay. And obviously we have different math, because this is the enigma here. I mean, depending on how far you go or what rate of time you go, because of the fact we're dealing with an exponential function, it makes a dramatic difference in this amount of curvature that you have to compensate for. So in other words,
go ahead.
I was going to say, so in other words, if a pilot is getting a little lackadaisical and he doesn't make any compensation for a few minutes, well, all of a sudden now he's dropping at a few hundred feet per minute. And like I said earlier, once you set your trim rate, you can go for a half an hour without ever having so much as plus or minus 50 foot in altitude change. So, you know, again, what we're debunking here is the idea that the pilot or the autopilot, either one, has to physically make changes. The argument that the other Globers make is much more sound and much more reasonable when they state that it is the gravity of the Earth that is constantly reorienting the plane center of gravity to the center of the Earth. And actually, if you look at it that way, it makes sense, right? But Wolfe isn't looking at it that way. Wolfe is saying that you have to make a physical correction, and this is exactly what we're going after here, because as a flat earther, I've always said you never have to make a correction in altitude, and this is in stark contrast to that. So
well,
anyway, go ahead, John.
we came up with the same 50 foot per second, and that was right on the money exactly. I got 49
on the first mile.
49.81 or whatever. I got the exact same thing. But the way I'm looking at it is, if you take any point in the flight after it's taking off and it's flying level, call that the base point. When it's flying level, that would immediately become a tangent to the curve of the Earth. And if you calculate this out to 1 hour, the way that I did it, and I can go through the math.
I've got 60 minutes right here, buddy. Here's my chart. Here's 60 minutes.
Right. Well, the way that I did it was, if you take 517, which is the speed of the plane, and square that, because that's the distance it's going to travel in 1 hour. Square that distance, and then multiply that by 0.666, then you get 178,779 feet per hour. And so that's what I mean by if that tangent line were allowed to continue. So if you didn't adjust for the horizontal whatsoever, that within an hour, going at 517 miles an hour, that tangent line would diverge almost 200,000 feet in an hour. And then if you divide that by 60, you get 2979 feet per minute. And if you divide that by 60, you get 50 feet per second.
Right. Absolutely. And this is why I said that this largely, how you're going to look at this depends on your particular frame of reference, okay? Because obviously you can take different times, different distances. The foot per minute descent is going to be all over the place. And this is the one thing that's really elusive about navigating a ball, if we were actually doing that. But you can also look at it, like I said, from a really crazy perspective, And yet, like I said, this is a perspective that cannot be debunked because it's just true. And so, like I said, if I go around the circumference of the Earth, 1/4 of the circumference of the Earth at 6,225.25 miles, and I'm in my 737 doing 518.75 miles per hour, I have a flight time of precisely 12 hours, okay? So now, during that flight time, I have dropped down the curvature, and I use dropped in quotes, of the Earth, 3,000 miles on the axis, okay? Now, I the following figure...
You broke up a little bit there just when you started putting out with the numbers.
Okay, let me begin then. All right, so if I'm going a quarter way around the Earth at 6225.25 miles, and I divide the 737's cruise speed of 518.75 miles per hour into that figure, I get a flight time of 12 hours. Now, during that time, I will also have dropped down the curvature of the Earth by one radius, 3,959 miles on the z-axis, okay? Now, I realize that the curvature follow-away figure calculated from the 8 inches per mile squared is exponential, meaning a little less curve traversed in the beginning and a lot more curve towards the end. So what I did is I said, okay, well, let's just average that descent rate. And we'll take the 3,959 miles descended within the 12-hour flight and dividing it by 12 hours, okay? And if I do that, then it gives me an average vertical z-axis drop of 329.9 miles per hour straight down, or 5.498 miles per minute, and finally a 29,031.5 foot per minute drop. Now, obviously that doesn't happen. Theoretically, it has to happen, right? Because those are the figures that were given for the Earth. But we don't really look at it that way. But yet it comes back to your particular frame of reference on how you're looking at it. So ultimately,
well, it reminds me of there's videos of military jets flying very, very close to the water, like they're almost, skimming the water. And if you think about this in a per minute sense, we're talking about, per second sense, we're talking about 50 feet per second. So every 10 seconds, those planes, flying level, which they're obviously flying level, should be gaining 500 feet. So yeah, it's just it's so preposterous when you actually look at it.
Right, and a small correction, that's 50 feet per minute, not second. But that, again, that is in the first minute. All right, that's just taking 1 minute, and you've got your 49,000 or 49.8336 feet, which is all hunky dory. So again, that it comes back, and of course, and I double check this with something that Kirk, Curious Life of a Flat Earther, gave me a long time ago, because when you get over a distance of 1,000 miles, or really I use 1,500 in an example, you can see when you deviate from the Sagittarius compared to the 8 inches per mile squared and versus the AutoCAD formula, they really start taking a massive departure from each other. You get down to the 3,959 miles, and of course, the 8 inches per mile square shows 1979, which is, not right. It's really 1819. And then he takes it all the way down to the 6225, which in the 8 inches per mile squared is 4893, but the Sagittarius gets it pretty close to 3965. So I even compared it to that. But the bottom line is what we're talking about here is there is a significant curvature that becomes exponential very quickly, especially when you're traveling at airliner speed. And you're right, when you have some of these Tomcats or whatever that are doing it at supersonic speed, maybe even going over 1,000 miles an hour, well then obviously that drop rate becomes quite a bit faster. And if those pilots are half asleep for even an instant when they're buzzing 3 feet over the water, they're dead, okay? That doesn't happen, and you will never hear any pilot saying, oh, I've got to constantly be, on that, right on top of it, because frankly, his reactions, I don't think, could even be fast enough to keep it right off the water like that without falling into it. So anyway, so I looked at that, and then I thought, well, okay, well, Wolfie, to be fair, is not using the 8 inches per mile squared or the Sagittar or whatever, what Wolfie is declaring is he's saying, well, it's 1 degree every 8 minutes of flight, okay, or a 7.5 degree per hour downturn, okay. So I did the math on that, and lo and behold, it comes out to be roughly pretty much what the exponential formulas we're using are. But then I talked to Rob Durham, who, as I said earlier, is also a pilot and an engineer and an AutoCAD whiz. And Rob Durham was nice enough to come up and model it on AutoCAD for us. So let's see what AutoCAD revealed to us for the parameters that Wolfie was talking about. And let's hear what Rob Durham, who is also an engineer and a fellow pilot, has to say about this. Let's bring this up. Oops, and
before we pop into this, since while we're leaving the last topic, I just had a couple things I wanted to cover. I already covered the major one, which was the feet per hour, which I thought was pretty wild. But he mentioned east to west circumnavigation. And of course, never north to south circumnavigation. That's impossible. But 48 hours. And I would just mention that west to east, as opposed to east to west circumnavigation, should be completely different duration flights relative to the, spinning Earth beneath, hypothetically. And the fact that 48 hours is the number regardless of east or west circumnavigation is really damning evidence against the spinning nature of the Earth. The second and final point that I wanted to bring up was, he mentioned the ant on the hour hand of the clock. That is just so, that's deceptive. Either he's inept or he's being deceptive, because centrifugal forces, there are variables that can be extremely important. Now, if it's one rotation per 24 hours, that's pretty slow. But like you said, when you extend the axis of rotation out to 4,000 miles, that edge, outside edge velocity is over 1,000 miles an hour. That's supersonic. And so he's totally missing the point that, yes, not a lot of centrifugal forces are created by the hour hand of a clock, but when you extend that that radius out by thousands of miles, then it's a horse of a different color.
That's true.
Hey, Bob,
and
just to let you know,
yes,
that Wolfie is in the chat.
And yeah, I can see him, and he just asked. He says, "Bob, do you understand why it's not exponential?" Well, Wolfie, that's the whole thing that I was just talking about at the beginning. To me, no, it never made any sense that it was exponential, because the curve is a constant thing. And again, this is where I can relate to what Charles told me, and also what Jaron said about when you turn a wheel on a car and you hold it there, then you're going to just basically carve tracks right back around in your own tire tracks. I get that. To me, it should be a very linear thing, but it is not computed that way, right? And also, because it's not computed that way, then that takes us back to when we're observing something allegedly going over the horizon. You guys say that the Earth is way too big to be able to perceive any curvature, and yet you stick to something as ridiculous as a 3 to 6 mile boat, of being 3 to 6 miles away, disappearing completely out of sight and going over the curvature. Of course, that's a whole nother argument, and we're not going to go there. So yes, Wolfie, I do understand that, and frankly, it confuses me, and this is precisely why I went out and hired 3 mathematicians that explained it to me in 3 different ways. And none of them really agreed with each other. And then, of course, there was Charles, who I have to say, out of all of the experts, on the globe Earth side, even though the other ones didn't know they were testifying for the globe Earth, Charles was very much the most helpful and had the best examples to kind of explain the baller side. So what I'm saying, Wolfie, is yes, I do understand this, but I think that you would be far better off with going back to the accepted ball earther argument of its gravity that is recentering the aircraft with respect
to... There's 747 people watching right now. That's so funny.
Really? Great. Oh,
747.
That's funny. All right, that's great. So anyway, yes, I get that. I totally get that, and that's why I'm saying. And honestly, Wolfie, I have every respect for you, but I had to call this one out because you are one of the only people ever that has admitted that a pilot supposedly has to compensate for the curvature of the Earth. Every other pilot says absolutely no, you do not, including the ball Earth pilots, which go along with this gravity argument. So yeah, I feel you, Wolfie, but you're just wrong. Okay, so let's continue on and let's play Rob Durham's and listen to Rob's take on this. Here we go.
Hey Bob, so this is what I've been working on since we spoke last night. So I've drawn here a 3,959 radius circle, and we'll start at this position, and assuming a height of 6.63 miles, which is 35,000 feet, I'm going to travel a distance of 69.17 miles in 8 minutes. This would be assuming that the starting position would be straight and level with the particular point it's above, and there will be no correction changes until after 8 minutes. So obviously the path of the plane and the Earth here are diverging since we're flying straight. This would be analogous to flying off into space. So it's at this position here, the second position after 8 minutes, that we make a 1 degree correction change, which is the angle from this green downwards to the new white line here. And you can see we were approaching at 89 degrees with this to this line here, and we're leaving again at 90 degrees. So we've made that 1 degree correction change. The result of that after 16 minutes is an increase in altitude to 7.83 miles, and this continues 8.44, 9.04, 9.64, 10.24, 10.85, 11.45, and then after 72 minutes we're at a height of 12.05 miles, and that is maintaining the 89 degree approach every time and the 90 degree new course. So it's double after 72 minutes. It's double the altitude that it was when we started. So that would be if that were the way he was proposing it's done. The other way, so I've drawn another circle the same, starting at the same height here, but this time instead of flying sort of into space, as it were, this time he noses down from this point, and assuming that after 8 minutes we're going to be at the same altitude at 6.63 miles, the white dotted line here would have to be such that it would be straight between the two, meaning in the middle, since there's a hump here, it's actually 6.48 miles. And this would continue. We'd still be, in this scenario, we'd be approaching at 89.5 degrees, and we'd be leaving at 89.5 degrees, giving us the same 1 degree change in attitude. So this would continue and continue and so on and so forth. So after your 72 minutes, you've still got the 89.5 degree approach and the 89.5 degree track. What I think the YouTuber is saying is that this green line here that I've drawn is actually the offset curve from here, just offset by 6.63 miles. So you can see it's kind of diverges away from this line. What I think he is saying is that this green line is the line that he takes, making very slight and gradual adjustments and corrections, and this is the line I think he's saying is not noticeable. It's not perceivable by the pilot that he's actually doing this, but he is. I think there would be too much of a bias on your controls. You would definitely notice it, I think, over distances like this. I think my biggest gripe with this is the fact that it goes against everything that globe earthers say happens. They say that there's no corrections needed and that gravity is the key to it all. That's what keeps the nose or the aircraft flying straight and level. There's no need for pilot correction. So coming from a professional airline pilot, this new revelation that they nose down is, in my opinion, is just completely erroneous. There's no evidence for it at all. Like you say, from his video, there's no indication from the attitude indicator or the vertical speed indicator that anything's descending at all. It never does. I've never experienced it. So that's my take on it, Bob. If you want to let me know if there's any changes you want to make or any other things you want to try on this.
All right. So there we have the take from another pilot, and we have just seen it demonstrated in AutoCAD. And this is the thing. Again, Wolfie, like I said, the pilots in either model do not compensate, do not actually make physical control changes to compensate for any alleged curve, okay? Even the ballers will admit this. And this is why I went after this, because you are in stark contrast to not only what your own people are saying about that this doesn't happen, it's gravity is doing this, but you're also in stark contrast to what the flat earthers, i.e. myself, a pilot of over 35 years, is saying and experienced, okay? So honestly, like I said, it's a much better argument to go with the gravity. Now, so what, again, this comes back to the idea of a frame of reference, right? Because as I have demonstrated, we can look at it in several different ways. So why don't we just apply Occam's razor to this and say, what's the simplest explanation? That the Earth is curved and gravity and all these things are actually compensating and adjusting the orientation, or that the pilot is making adjustments that would be tantamount to very large vertical course corrections, whether it's done in small blocks of time or great blocks of time. Of course, that is completely blown away by the fact that, you know as well as I do, when you trim that aircraft out, you can fly for hundreds of miles without ever having to make any correction whatsoever. Now, of course, your response to that would be something like, oh, well, you just got lucky and hit that trim, so it's perfectly making the adjustment for you, which, of course, I'm saying, come on, let's get real here. All right, that's not what's happening at all. So how do we break this stalemate? I mean, well, first of all, if we don't solve it by Occam's razor, you know, and take the simplest explanation, which of course would be the flat Earth, and of course I have a lot of, I'm watching the chat and I'm seeing a lot of people say, oh, are you saying gravity doesn't exist? Yes, we are. We're saying it doesn't exist in the way that you guys have been taught that it exists. And if you want to go back and look at not only my explanation of what gravity actually is, but some of the other physicists, going all the way back to Tesla, and understanding that the notion of what we're calling gravity is actually an electrostatic force that is provable and demonstrable that's being generated from the plane Earth itself. Well, there's your gravity, okay? But so Occam's razor aside, even if we don't choose to take Occam's razor and we want to accept that gravity is doing all these measurements, what's going to be the stalemate? What's going to be the tiebreaker here? Well, the answer to that, Wolfie, is the gyroscope, all right? It's a gyro. Gyros stay rigid in space. Not all aircraft have Schuler tuning mechanisms, and the pendulous vanes is not a legitimate argument for saying that that is what's compensating for the correction of the gyroscope. Because if it was, Wolfie, then we wouldn't need a Schuler tuning mechanism now, would we? Okay, so let's just kind of eliminate that there. And what we're going to prove with our pilot is we're going to put an independent gyro in an airplane, and we're going to go flying straight and level, and we're going to see if there is any precession in that gyro. Now, we already know that the gyros don't precess on the ground, even though Leon Foucault said that it did in his 170-year-old gyroscope. Leon Foucault was a liar. All right, because it doesn't happen, and we have far better gyroscopes today than he did. Okay, secondly, I want to mention something that Rob Durham is doing, and I'm not going to mention a whole lot about it, but look for this soon, guys, because when we were on Skype yesterday, he showed me a really cool way that he rigged up his gyro to kind of dismiss the argument of, oh, the gyroscope is not sensitive enough to detect this precession. And in other words, the argument that's being brought back and thrown at us is that, well, there's too much of a mechanical bind for the gyroscope to be able to show any precession. So Rob Durham's answer to that, which was brilliant, is he suspended it via threads, okay? which means, I mean, it is now so unbelievably easy to turn around that, you know, a slight breeze of wind will do it. So when he does his experiment, he's obviously doing this, and what he told me happened is that when the gyro spins up, it kind of goes back and forth, and then it kind of hits an equilibrium, a sweet spot, and then it is solid as a rock from there on out. Never precesses, never moves, never anything. Furthermore, he went and bought, there's an old Navy training video out there that's all about gyroscopes and how they have to precess and all this stuff. And they did a whole video about it from the Department of the Navy. Well, guess what? Rob went and bought that very same gyro, and he spun it up. And his initial results, and he had just gotten it, I think, yesterday or the day before, his initial results were, guess what? No precession. Why? Because the Earth is not moving. And our aircraft indicators tell us exactly the same thing, Wolfie. They are gyroscopic in nature, and whether your corporate plane has a quote-unquote Schuler tuning mechanism or not, you know as well as I do that you were licensed, well, you were licensed 5 years after I was, from what I read. And back then, they didn't have computer systems that modified navigation systems, you know, for Schuler tuning. They didn't have it. It was purely gyroscopic, just like most general aviation aircraft is today. So what is the tiebreaker? The gyroscope. The gyroscope proves unequivocally that there is no rotation to the Earth and there is no curvature to the Earth, because I got news for you. Your gyros, after 12 hours of flight, are going to show a 90 degrees orientation shift when you get done taking your little plane flight. It doesn't have to, you don't have to go all the way around the plane. 90 degrees is more than enough. 45 is more than enough. Actually, a lot less than that is more than enough, because 0 is 0 is 0. If there is no precession after 5 minutes, and no precession after a half an hour, and no precession after an hour, then there's not going to be any precession after 12 hours. It's as simple as that. So that is my presentation, and you know, what do you guys think about this? I mean, what kind of feedback do we have here?
Yeah, no, that's awesome. I sort of made my couple points interrupting you so rudely, but the whole argument about pilots having to angle their noses down in order to compensate for the curvature of the Earth is just so ridiculous. Airplanes are named because they literally, you know, once they've taken off and they've reached their sort of cruising altitude, they obviously fly along a plane. And it's, you know, like you said, when you're well balanced out, you really don't have to adjust for the horizontal axis much. You know, if it's relatively, you know, good clear skies and everything. And so yeah, it just totally goes against any notion of sphericity. A level flying plane should technically be flying at a tangent to that curve, which would be, as you said, increased exponentially with your speed. And you know, pilots just simply don't see that. So it's to me, it's self-evident. So yeah, good work, and I always love Rob Durham's work. It's really well presented, and yeah, awesome.
Yep. So there you have it. Okay.
Yeah, no doubt. Good work, Bob. I think it's impressive, or not impressive, but it's kind of important that we notice that things like Honeywell is the company that produces all the equipment, that is found in every plane. Just like I just found out recently that there's one company that produces every window of every plane. So, I mean, things like this are the kind of thing that should be red flags. It's not what would go on in a real world where you would say there's all these different planes and all these different Boeing and there's, different jet makers, and how could they all have the same exact manufacturer of the windows? And there's reasons for these things, and the reasons point every single time to deception. To, they're going to curve off the windows so that they look round. This is a huge deception, and it's spread all over, and it's noticeable. Once you realize what they're up to, everywhere you look, it shows itself. Everywhere you look. I mean, I think that there's even a problem with the whole curvature formula still. I don't bring it up much anymore, but I still go back to the same thing, that it does not make any sense, anything of what people have been saying, that you can take like you said, in the 6225, that drop is using the 8 inches per mile squared at 4892, and I know people say, oh, you can't just take that section and divide it up into 10 segments. Well, obviously not based on that formula, because when you do,
right, you're missing out on that exponential factor. Yeah.
But I still don't understand where they get the exponential if in other equations they say we're always at the top of the ball. So wouldn't you just always rotate the ball underneath you in that fashion? You know what I'm saying?
Yeah, absolutely. And that's what I was saying. And that's why it confuses me. Wolfie asked the question, do you not understand, why it's not an exponential function? It's like, well, yeah, it seems like it shouldn't be, because again, it's a linear curve, but it is only defined mathematically for in exponential terms. And this is the funny thing, out of all of my experts that I hired, guys, not one of them could come back and give me an equation that would solve for any continuous rate of curvature, to solve this 6225 mile forward x-axis to the 3959 z-axis drop. Nobody could do it, which blew me away, right? It's like, how can you not be able to describe that and come up with a solution? That's like saying that if I'm driving around in circles in my car and I'm holding the steering wheel at so many degrees of right turn or left turn, that you cannot define mathematically or express or predict, where the car is going to go. And to me, that's crazy. I just don't understand that. So
I'm
with you, Jaron.
It doesn't make any sense. I mean, you should be able to describe it since it's, now, again, I'm talking about a perfect sphere. So we're not talking about mountains and valleys. Let's just say it's a perfect sphere. That
right.
Each segment of curvature is the same. It has to be. That's the whole definition of a circle. So the way they draw it, and this is even crazy, I think I've shown it before, when you look at pixels, if you take a circle and draw it on a computer program, the top of the ball and the bottom of the ball are flat, but the sides never flatten out. But if it's a circle, you should be able to turn it, and the sides become the top. Well, sorry.
Yeah, that can be taken care of with anti-aliasing.
With what?
Anti-aliasing. It's sort of to smooth out like like angular lines on low resolution will look like sort of a bunch of sort of semi-parallel lines. It won't look like a smooth angled line. While anti-aliasing is like a computer function that can get rid of that.
Got you. And you're just describing my point exactly, is that a circle would have to be perfect curves at all places, but they describe it as, well, when you're looking out from your first 8 mile, it's only 8 inches of drop, and then from there it grows exponentially. But that's describing the ball like you get on your computer, that has a flat line on the top and then starts to curve and grows exponentially. It just doesn't make any sense that it would not be something that you can't cut up and take each individual section and say, if you have 24,901 people lined up North Pole all the way to North Pole, and you were going to measure from each person according to the formula that we're given, there would only be 8 inches of curvature between each person. Each person would measure from them to the next person, them to the next person. So each person would come up with 8 inches, which going over the entire circumference of the Earth would be 3 miles of curvature. It's ridiculous. I mean, that's not correct. And yet they'll say, no, it is correct because it's exponential. It grows. Okay, well, why can't you have a number that would be from person to person? And I believe we have come up with that number, and it's either 0.318 miles per mile or 0.634 miles per mile. One or the other. I'm not sure which one we.
Yeah,
it's because
318 is what you got, Jaron.
It's because the curve is dropping away at a further, faster rate at the second or third mile than it is at the first mile.
Okay, but here's what I'm saying. So this is what I'm saying, John, is that if you have people, 24,901 people lined up North Pole to North Pole, they're going around the Earth. You're saying that between the second and third person, that there's more of a curve for them, but they're only measuring 1 mile. So how is it any more of a curve for them than it is the first and second person or the 50th and the 51st? Everybody's measuring the same mile. You can't say, oh, well, person number,
let's just say you're dealing with 3. You've got 1, 2, and 3. Okay, 2. If you're looking at 2, 2's on the top, 1's to the left a little bit lower, and 3's on the right a little bit lower, right?
No, I lost you. Hold on. Just take it as you have one person every mile all the way around the Earth. So you've got 24,000.
Well, no, just like say 3 people 1 mile apart.
Okay.
All right. 1, 2, and 3. 1 on the left, 2 in the middle, 3 on the right.
Okay.
Okay. If you're focusing on 2, then 2 would be on the top, and 1 and 3 would be 8 inches lower. But if you're looking at 1 on the top, then 2 would be 8 inches lower, but 3 would be 16 inches. Yeah, whatever, 16 inches lower, 32 inches lower, whatever it is.
What if you're just measuring from 2 to 3?
Then it would be 8.
Okay, so what I'm saying is
because it's a tangent line that's the curve is going to be divergent exponentially from that tangent line, but only from one single base point. When you change, of course, when you change that base point, then it's going to change with it.
Right.
That makes sense.
Yeah. So what you're saying is that we would, each person, all 24,901 people around the Earth, would each measure 8 inches of drop per their individual sections. Correct?
Yeah, compared to one another. Yeah.
Compared to one another. Right. Which that's only adds up to 3 miles of total curvature over the entire Earth.
Yeah, no, I see what you're saying, but again, it's subjective. The 8 inches per mile squared is subjective, and it only works if you use one single base point. If you have multiple base points, then it doesn't work.
And that is exactly right, John. And that's exactly why I said it all comes down to a frame of reference.
Right.
Where you're going to take that frame of reference. And it screws with your head. Believe me, the last 2 weeks between the math experts and me just sitting there going over this and considering what you've said, Jaron, and also looking at the examples that Charles gave me, I just said, you know what? I don't really want to even try to defeat this with math because the math can be outrageously variant, right? From anywhere from 50 feet to 29,000 feet per minute, right?
Right.
And anywhere in between.
What it seems to me is that the reason why things aren't coming out in astronomy right now, like the background map, the microwave background, is because it proves that there is a top and bottom in space. And they can't let that be known because once you have a top and bottom in space, you have an up and down, you have preferred directions, which the map shows. It's clear that it shows that the Earth is in the center. It's clear that it shows that there's a preferred direction, which means there is an up and down in space. And as soon as there's an up and down in space, everything you've ever learned about astronomy in your life about the Earth is gone. It's gone because you can no longer say, well, we just turned the ball. Oh, it's all subjective. You get to put yourself at the top of the ball every time. No, you don't. And it goes back to me saying over and over again that I can live on a ball and you can live on a ball, but we cannot live on a ball. It's absolutely, positively impossible for human beings in a group to all live on a ball. Because in order for that to be true, we would each need to take the center top location and have our lives operate from that point, which is why they describe space as there is no up and down. By them saying that, then it allows it to happen where you have to say, oh, well, I guess from each of our perspectives, we are the top of the ball. But now when you're hearing from these microwave background maps that there is a clear top and bottom, there's a clear middle, then therefore there is a top and bottom, which means you can't go off that anymore. And that's why these things are hidden. I mean, you said about gravity earlier, you said somebody in the chat, excuse me, said, do you guys believe in, you're saying gravity doesn't exist. I mean, think about what scientific testing is supposed to do. I've heard Lawrence Krauss say it 1,000 times. As soon as something is proven wrong in the lab, you kick it out. You throw it out. It's proven false. Well, guess what? They've proven false gravity every day they look at the universe. Every single day, gravity doesn't work. So what did they do? Did they kick it out? Well, of course not, because if you kick it out, we don't live on a ball anymore. There is no center of the earth. There is no stuff that pulls everything to the center. So what did they have to do? They made up shit. Dark matter, dark energy, 97% of the universe never been observed. This is what happened. And people like Charles, Flat Earth Math, all these guys are arguing on behalf of liars. It's sickening. Wake up. It's right in front of you. All the answers are right in front of you.